We heard a lot about the different realizations, how we can do the whole system design from bits all the way to the antenna, from the concept which was used, from the simulation and everything. But to a certain degree, sometimes that also has to be, I want to say, verified. A model is good. A model is always an approximation, but you want to understand how good is the approximation. And that is where real test and measurement comes in. And also when you do the overall design, you want to verify, as Matt mentioned, the different components which will go into it, as well as on the system level, when everything has to play together, does it really play well together? So what I'm showing here is basically the flow of the whole RF chain all the way from an FPGA on the left side towards the antenna on the right side. And what I want to highlight here, or what I want to go over there is that flow is basically the same as what we've seen before in a little bit of a different variance, but it's basically exactly the same which we've seen before. And what are the real key points with regards to signal integrity, but also on the system performance level, because we want to make sure that all pays into having a good overall system performance. So when we are talking on the digital side, well, there is this digital processing, which can be in hardened devices, which can be in an FPGA. In that case, which is discussed here was the RF SoC. It's kind of a combination between both because it's all integrated into this RF SoC. And basically the first two blocks was the FPGA and the baseband processing, as well as the ADCs, all integrated into this RF SoC. And what you want to look at here is all the interconnects in and out, because the FPGA in here is just taking the payload, the data which needs to be transmitted. So they need to arrive in a really good fashion. So it's about understanding the data which comes in. So it's about the power and signal integrity, because it's the signal integrity when the signal comes in. So you have a clear signal coming in, as well as if there is any variance on the power supply of a D2A converter, you directly see it at the output of the D2A converter or at the digitization. So if there is a little bit of a variance on the power supply, you see it straight away. So signal integrity does not only count on the data which you send in and out, but also on the power cleanliness which goes in and out. Often forgotten case. Obviously also the clock tree which drives it and the SERDES which drive into it. When we talk about the data converters, we heard before in this PAM module, it's not only one antenna, but it's multiple. So multiple antennas means they need to play in concert at the right timing, at the right speed levels. So making sure that the amount of different HD converters is very well aligned, which is pretty simple when we are talking about the RF SoC and we're using just the A to D converters or the converters inside of it. And last but not least on the data converters, well, they also can create a good amount of noise based on the clock which is used, as well as the purity of those devices. The signal which comes out of the data converters, D2A on the transmit path, we saw in the beginning from Luc that depending on which Nyquist zone you're using, you want to make sure to filter out all the other stuff. So that is where this filter comes in. Need to make sure that the filter has the right A performance steepness and the right blocking characteristics. Then, when you put everything in together and drive it up, you have this the up and down converter, which we've seen also with the Otava system, which was designed here together with Avnet. And this phase behavior needs to be translated. So it's an up conversion. So you drive digitally on the baseband side, the phase. You drive digitally the phase here, and you need to understand that when the mixing goes from one frequency to another, how the phase relationship is at low frequency, IF, up to the wanted frequency, 24, 28 gigahertz, 30 gigahertz, depending on the application, if we're talking about a 5G FR2, if we're talking about a SATCOM application. And once we are going into the beamformer, obviously on the beamformer, there is the whole thing of all the RF stuff. So you need to ensure, you have very good control of the phases, that all of these settings happen basically in real time, ideally. When you want to do a change from one direction to another, because that is an important thing. The other way, when we are talking about a satellite link, you have to follow very quickly those satellites, because when we are talking about geostationary satellites, then it's easy, they are not moving. But if you're talking about low Earth orbit satellites, like all the NTN systems, all the small cubes, they are much lower in altitude, probably only 800 kilometers up there. So they fly across Europe's point when you see them only for a couple of minutes, and you have to follow very quickly. And then at the end, you have to jump back instantaneously. So how fast can you do those jumps? A thermal management, that is a very important topic, because in those beamformers, there are 4, 8, 16 channels, depending on the different variances. And very often there is also a fully integrated of the RF front end, meaning the amplification stage. Amplifiers have the tendency to not only amplify the signal, but also to create a lot of heat based on the efficiency which they have in. And those beamformers using high integrated multiple channel, there's a lot of heat dissipation. So the cool and the thermal management is really an important topic on those ones. Last but not least, going into the antenna, well, it's about the beam directivity. How exactly can you form the beam? How is the beam look like? And crosstalk is another one. And crosstalk is actually not only on the antenna from one patch to the other, but for the overall system from all the different lines. And that comes back towards the signal integrity, because crosstalk can happen not only on the digital side, but also when you have multiple of those RF lines going from one block to the other, where exactly also the design from the connectors, as Matt discussed before, really makes a big importance and makes an important step to look into closer, because you want to understand that there is no crosstalk, or at least minimize the amount of crosstalk. Coming to some of those solutions which we are talking about. On the digital side, well, obviously, at first you think always about jitter. Jitter is a time domain thing, so you're looking at how can I make sure that I have a right eye opening. That's typically the measurement for understanding you have a low enough jitter, so you can understand very well the different positions of the signal. So that's typically a scope measurement. Now, when you think on a connector, how can you make a measurement just with a scope? Basically, not really. For a scope measurement, you need to have the whole signal flow which runs through. If you want to understand the signal integrity of a line on the PCB or of the connectors, you need to go a little bit in a different route, and that is when a VNA, a vector network analyzer, comes into play. You might think, vector network analyzer, those are RF devices. How does this make sense with jitter measurements? Well, they also have the ability to do time domain analysis. So you have a 2-port device with an input and an output, and it basically can measure based on the S parameters, do an internal Fourier transformation over towards time domain, and represent then also directly here giving you the eye diagram measurement. So a VNA is the right approach when you go into passive devices with an input and output and verify all of those things, like PCBs, cables, connectors, and whatnot. And obviously what can be measured, it's about the matching, it's about the impedance. Crosstalk, when you have a multiple port, I'm coming to this, a multi-port device, you can see directly, what happens between, I'm sending a signal on this line, what do I see on the other line? Because there can be always crosstalk. And then last but not least, the eye diagram, which goes into it. Okay. A VNA and doing measurements always requires at first a reliable calibration of the system. So how do we do a calibration of that system? Typically, a VNA has its own calibration routine, fully integrated. There can be an automated calibration module or a manual calibration. Both ways are possible. But when we come down to the DUT, in the case of, for example, a connector or a PCB, we cannot always just get a nice whatever SMA connection towards our DUT. Maybe there may be some lead in, lead out, and you cannot directly go towards the connector which you want to verify. You only have a thing which is a little bit further out, and you want to take this out of the measurement because you only want some internal side. So you have to do some way of removing the effect outside. And that's exactly what de-embedding is about. So you want to understand what the effect is of what you don't want to see. But it has some effect because the whole system, always everything comes together. So this is exactly why de-embedding is an important thing. You only want to understand the performance, the characteristics of one piece, and everything outside you want to take out. There are different routines. There is a dedicated also calibration approach, so to speak, with a through approach and calibrate out. And there are different algorithms fully integrated into the VNAs, at least from ours, which allow to take out, based on different algorithms, the effect of everything outside. Multi-port device. I mentioned before when you have a connector with many connections, like what Matt has shown before. It's not only like one in, one out, and then it's easy, all good. No, those digital design boards, those digital boards have a lot of connections on the digital lines, maybe even also on RF lines, all on the same connector. So you want to understand how well those are working with regards to the different lines, how well can they handle it, as well as is there any crosstalk? Because the digital signal may be a rectangular, the RF signal may be a sinusoidal or a modulation already on it. Obviously, there shouldn't be any crosstalk, ideally. And when you use a standard VNA, 2 or 4 port, there's a good amount of different switching needed, which can be done very nicely and do all those measurements. But you have to keep in mind there's a lot of ports, so you're doing one after the other. With a 4-port, at least you can see the crosstalk from one line to the other. But with all those, in this example, 64 connections, 64 ports for 32 lines, there's a lot of consecutive measurements. A multi-port device, like what is shown here with the ZNBT, which can have up to 24 ports. Here in this example, it makes sense to just go for a 16-port because this way you can do nicely a combination of those sections and make much faster measurements, faster verification, as well as get more information about crosstalk. Okay, coming to the system level design. Once we know that all those parts are by itself working fine, we want to understand that the system level works. And as we have seen before also from Luc, one method, one key indicator is to look at the overall system level EVM. How to measure these? That is exactly, I want to say, kind of a reference system in the industry with regards to getting industry-leading performance capabilities to measure EVM on those systems with a signal generator which provides the RF signal for the receive tests and with an analyzer for the transmitter tests, or when you have an active device like just a beamformer by itself, you need to feed it, you measure the output. Exactly the same thing. The signal generator, the whole system has a bandwidth coverage of 2/4 gigahertz based on the signal generator. The analyzer by itself could go even up to 8 gigahertz with frequency ranges of 67 on the generation side and 85/90 up on the analyzer side. What is interesting is that this system not only gives you EVM numbers, but when you do a system level design, you want to optimize the whole system. To get more efficiency out of the RF front end, you typically apply, or you typically use the RF front end close to saturation where they are doing, where they are getting into compression. So you also want to apply some form of linearization, DPD, which is possible with this one because there is the ability to refer to the DPD and to see how good a system can be when it applies ideal DPD, so to speak. Again, the same thing for the beamformers. Here there is the difference between a high-end vector network analyzer, which is shown here, giving you maximum sensitivity, maximum resolution, 4 ports, versus a multi-port device, which allows a much faster measurement. So it really depends on the application, what you're interested in seeing. Last but not least, coming again to the system level design, putting everything together. The PAM has an antenna on one side. How can we connect to that one? That is where over-the-air measurement comes into play, and you want to have these in a, I want to say, controlled environment. There are different approaches. Actually, 8 different chambers, different controlled environments, as well as how to measure with those. The concept is always the same. You need to have a defined OTA system, plus connect instruments as before, as I mentioned. So the upper side is basically with continuous wave using a VNA in order to characterize the beam characteristics, the antenna characteristics, measurements of EIRP, beam capabilities, and so on. The lower one is looking at the system performance using exactly, again, the same as the signal generator and analyzer, and measuring the EVM performance or all of those performance matrices which are applied. And just a quick overview about the different OTA systems. 2 of them are also down at the show floor. It's basically a differentiation between a direct far field, because ideally we want to make EVM measurements, so we have to go into the far field. If we only make measurements on the antenna characteristics, that can also be in the near field. At these frequency ranges, far field means 2 feet roundabout, 1 to 2 feet of a distance. And that is pretty much applied in all of these. The ATS 1000 gives us nice characteristics on that one. Also being able to use temperature testing. So there could be a temperature bubble inside to do environmental testing across the whole system. While the other 3 on the left side, they're using a little bit of a different approach. It's not a direct far field system with an antenna pointing towards the device under test, which creates a relatively small area where you have a perfect far field condition, but they're using a CAT-R approach, which increases the section, how good, where you can make measurements, and that defines basically if the antenna, if the PAM is getting larger with more modules, you want to have a larger quiet zone, as this is defined, as this is called, in a way to have the ability to measure the whole system in the right way. Okay, with this, I want to close my part and say everything is possible, but we have to work together to make it happen.